we are taking the really complex theoretical side of expert network configuration and boiling it all down. We want to get to the pure, actionable architectural insights. So for a moment, forget about the certification exams. We're going to dive right into the details that, dictate whether a high-performance system actually works or just falls apart under pressure.
That's absolutely right. I mean, when you're operating at that kind of scale with that level of security, success isn't just about knowing how to set up BGP. It's about knowing that one single command that you can't get wrong, the one
Yeah.
that makes the whole thing stable across a huge dynamic network. So today our focus is really on pulling out those core architectural rules that are sort of hidden inside this very technical source material.
And our sources today are a set of practice questions for the NSE 8812 expert certification. But look, we are not here to quiz you. Our whole mission is to understand the why. Why these specific settings matter so much for things like high availability, dynamic routing, identity, and even how the hardware itself works inside.
Yeah, think of it as us translating these, high-level configurations into something tangible. We're talking about FortiGate hardware acceleration, BGP route reflectors, zero trust, all of it. We want to give you a practical understanding of the system's logic. We're going to show you those critical points of synchronization that can make or break a secure fabric.
Okay, let's unpack this. And let's just jump straight into the deep end with dynamic routing. Because if you're building any kind of next-gen secure network, you're almost certainly using dynamic tunnels, probably ADVPN, and that means your BGP configuration has to be, well, surgically precise.
Precisely, yeah. So let's take a common ADVPN setup. You have a hub, it's acting as a route reflector for a bunch of spokes. And of course, you want those spokes to talk directly to each other, right, without sending all that traffic back through the hub. This requires internal BGP.
So if we want those spoke-to-spoke shortcuts to actually connect, to negotiate successfully, what is the one setting on the hub you absolutely have to get right?
The hub must have the BGP setting route reflector client with next hop unchanged enabled.
Okay, so why is that one command so critical? Why is it so foundational? Doesn't a standard route reflector usually change the next hop to its own IP address when it advertises a route?
It does, and that's exactly the problem here. In a normal routing scenario, that's fine. But for dynamic IPsec tunnels, the spoke needs to learn the original next hop. It has to know the actual tunnel endpoint address of the other spoke it wants to talk to.
Yeah.
If the hub changes that BGP next hop attribute, it just breaks everything. The tunnel negotiation fails because the peer literally doesn't know who to talk to. So this command, it preserves that integrity so the tunnel can actually come up.
That is a perfect example, a setting that seems so minor, but it's architecturally indispensable. Okay, let's shift gears a little bit. A really common real-world problem influencing traffic that's coming into your network. Say you have two different upstream ISPs, but they are ignoring your BGP MED attribute, which, happens all the time. How do you tell the rest of the world, hey, send your traffic through this link, not that one?
Right, so you can't rely on them to do you any favors. You have to use an attribute that is globally accepted. And that is the AS path. The solution is something called AS path prepending.
Prepending, that sounds wonderfully deceptive. Why does that work when MED fails?
Well, it's really just down to BGP's core path selection algorithm. It's simple. You artificially make the AS path longer on the link you don't want traffic to come in on. So on your less preferred link, link B, you just prepend your own local AS number again and again and again.
So you're basically making that path look less efficient, less desirable on purpose.
Exactly. You are making your own route look bad to influence your neighbor's decision. BGP, by default, always chooses the shortest AS path. So by making link B's path look artificially longer, external networks will almost always choose link A. It's the most reliable tool you have for influencing inbound traffic.
Okay, so we've established how critical that external synchronization and path metrics are. That's a great segue into chassis performance, because once that traffic hits your device, internal consistency is just as important. Let's look at the architecture of, say, a high-end FortiGate 7000 series.
Right, 7000 series is a multi-module chassis, which means traffic has to be distributed intelligently across several different processing units. We call them FPMs, or FortiGate processor modules. And the component that does all this high-speed internal steering is the integrated switch fabric, the ISF.
So what is the ISF's main job, architecturally speaking, when it's handling all that throughput?
Its primary job is session-aware load balancing. And this is really complex, but it's absolutely critical for any kind of stateful security. It makes sure that every single packet that belongs to one single session, say one long HTTPS connection, is always consistently sent to the same processor module for its entire lifetime.
And why is that consistency so vital? Can't the modules just share the security state?
Well, they can, but routing traffic randomly would just kill performance. Not to mention session continuity. The FPMs maintain their own local session tables. They have the context for their flows. So if FPM 1 applies a firewall rule or a NAT translation, all the packets that follow have to go to FPM 1. The ISF is the glue that holds all that logic together. It's like a high-speed, session-sticky traffic cop inside the box.
That internal consistency is definitely key. Okay, let's turn to high availability, or HA, and how these choices affect resilience. We talk a lot about synchronizing sessions, but what happens when a team decides, you know what, we're going to prioritize performance? They go in and explicitly disable session synchronization in their HA cluster.
This is a classic trade-off. It really shows the tension between performance and resilience. If that cluster is configured with session pickup disabled and the primary unit fails, the result is instantaneous. All the sessions are terminated.
Wait, so you're telling me that this choice, this architectural choice to, say, minimize latency, results in a hard failure? The sessions are just dropped.
Yes. They're immediately dropped. Poof. Gone. The secondary unit, which was just sitting there in standby, it didn't receive any of that synchronized session info. So when it takes over, it has zero knowledge of any of the ongoing TCP flows, NAT translations, nothing. So every single client out there has to reestablish a brand new session from scratch. It's a very fast failover, but it's really messy for the user experience.
Wow. That really makes the cost of that performance optimization very, very real. Okay, so we've seen internal sync, routing sync. Now let's talk about the synchronization needed for trust and identity.
This brings us right into the world of SAML security assertion markup language. SAML is, fundamental for single sign-on. A super common, super frustrating error is when a user is logging out of an app and they get a SAML 20 logout error, a timestamp validation failure.
Okay, so if they're just logging out, we know their credentials are fine. What's the painfully simple cause of that failure?
It is almost always a significant time skew between the service provider, which is the application, and the FortiAuthenticator, which is acting as the identity provider. SAML is incredibly unforgiving about time.
So time itself is a security component in SAML. Why is that?
Because the SAML assertions, the requests, they all contain timestamps that define how long they're valid for. This is what prevents replay attacks and makes sure the assertion is fresh. So if the clocks between the SP and the IDP are not synchronized, ideally via NTP, the system receiving the message will just reject it. It sees it as either expired or from the future. Synchronization isn't an option, it's a prerequisite.
That focus on time sync really echoes in cryptography too, especially with IPsec VPNs. So if you're troubleshooting an IKE Phase 1 negotiation failure and the debug log clearly says no proposal chosen, what two things are mismatched?
The two main culprits are either a mismatch in the DH, the Diffie-Hellman group settings, which means they can't agree on the math for the key exchange, or a mismatch in the encryption or hashing algorithms.
Okay, now here's where it gets really interesting for anyone troubleshooting this. Why isn't the pre-shared key, the PSK, on that list? I mean, isn't that the most common mistake people make when they set up a VPN?
It is the most common mistake, but the proposal failure happens logically before the PSK is ever even checked. Phase 1 is like the cryptographic handshake. It's where the two sides agree on the secure methods they're going to use. If they can't agree on that shared crypto suite, the DH group, the cipher, the hashing algorithm, the negotiation just fails immediately. Seeing no proposal chosen is actually a huge clue. It means you can stop checking the PSK and focus only on those Phase 1 parameters.
That's a critical tip. It could save hours of time. Okay, let's shift to segmentation and how we handle traffic inside a single appliance using VDOMs, or virtual domains. If we need traffic to move between VDOM A and VDOM B on the same box, what are the two main ways to do that?
You basically have a choice between two different architectural paths.
Yeah.
Internal virtual routing or external physical segregation.
Yeah.
So the internal method is to configure a virtual VDOM link interface. This creates a logical point-to-point link inside the box. It functions just like a router interface and lets traffic flow directly between the VDOMs.
And the external option, which seems a little counterintuitive for single bot.
Right, that is literally connecting two physical ports on the outside with a cable. Each port is assigned to a different VDOM. People call it hairpinning or loopback. And while, it uses up physical ports, it lets you apply full Layer 3 routing and policy inspection on that traffic as it leaves and comes back in. You're treating the inter-VDOM traffic exactly like external traffic.
So you choose internal for simplicity and performance, but external if you need that maximum policy-driven control.
Precisely. Now let's talk about protocol transformation, specifically NAT64. We need to let all these IPv6-only clients get to the massive world of IPv4-only servers. And this isn't just a simple firewall rule. It needs two very specific interconnected pieces to work.
So what are those architectural requirements for NAT64 to actually function?
Okay, requirement number one. A dedicated NAT64 prefix has to be in use. Usually it's the well-known 64.ff9b.96 prefix. This is the mechanism that embeds the destination IPv4 address into the IPv6 request itself. But that's only half the story.
And the second half has to do with name resolution,
Yeah,
right?
exactly. You need DNS64 functionality, either running on the firewall or on an external server. The IPv6 client, it can only ask for a AAA record, an IPv6 address. If the server it wants to reach only has an A record, an IPv4 address, DNS64 has to step in and synthesize a temporary AAA record for that client.
Ah, okay. So the client is asking for an IPv6 street address, but only an IPv4 house number exists. DNS64 is like the mapping service that pastes that NAT64 prefix onto the house number to make it look like a valid IPv6 address, and that allows the client to even start the conversation.
That is the perfect analogy. Without DNS64 creating that AAA record, the IPv6 client never even knows the destination address, so the conversation can't start. It is absolutely mandatory.
That's pure protocol translation mastery. Okay, before we get to zero trust, let's just quickly touch on threat detection. The intrusion prevention system, the IPS engine. What are the two core tasks that the IPS engine is doing that are different from, say, a standard firewall check?
So the IPS engine is really focused on two things. First, it performs TCP/IP protocol anomalies checks. This means it's looking for anything that deviates from expected behavior, malformed packets, weird flag settings, anything that hints at a low-level exploit.
Okay, so it's checking the health of the connection itself in the second core task.
The second is the classic role. It actively matches traffic patterns against its known signature database. This is where it identifies known exploits, specific malware, buffer overflows, and things like that. Both are absolutely essential for real protection.
Finally, let's wrap this all up with the architecture of a modern security fabric and zero trust network access, ZTNA. ZTNA policies rely on really granular endpoint posture, knowing if a user's machine has the AV installed tag, for example.
Right. And to make ZTNA work, to actually use those dynamic context-aware tags on the FortiGate, two specific fabric components have to be working together perfectly.
So what's requirement number one? Where does that posture information come from?
The FortiClient must be registered to the FortiClient EMS, the endpoint management server. The EMS is the brains of the operation. It's the system that's constantly checking the client's security state and generating or updating those dynamic tags.
And how does that critical health information get from the EMS over to the firewall, the FortiGate, which is where the policy decision is actually made?
That's requirement number two. A fabric connector must be configured on the FortiGate specifically to talk to the EMS. This connector is the synchronization link. It pulls down all those dynamic endpoint tags and their status. This is what allows the FortiGate policy to read an attribute like AV installed and enforce an access decision based on the current context of that device, not just its IP address. And leave you with a final thought. Reflect on that dichotomy we just discussed. In the core network, we saw that disabling session pickup in HA causes a hard failure. Sessions drop. You accept that for speed. Now contrast that hard failure with the policy-driven decisions of the zero trust model we finished on, which demands perfect, context-aware policy decisions at the edge. How does an organization successfully transition from accepting session drops in their core infrastructure to, at the same time, demanding seamless context-aware continuity for their users? That's the tension that's really defining modern security architecture, and it's something for you to mull over.